Hello again. This is the beginning of session number 7, where we are going to introduce briefly the geometric dimensioning and tolerances, what is called GD&T. So what is GD&T? GD&T is a system of dimensioning and tolerancing mechanical parts, uh, which allows parts to fit and function at the assembly level. So normally, after we just manufacture individual components, in order to make them function properly, we need to assemble them. And in order for those individual components to just fit together correctly and function correctly, we need to have some sort of system in place so that we make sure that the dimensions and tolerances are correct. This is where the GD&T comes to play. So in engineering drawings that we create for a manufactured part should convey some sort of information from the designer to the manufacturer and the inspector. So that they don't come back to us and ask about specific dimensions or specific tolerances. So these engineering drawings must contain all the required information that is necessary to correctly manufacture the part. And also those information enable the inspector to precisely check or inspect the part and decide whether this part is acceptable or not. So each engineering drawings must convey 3 different essential types of information. It should convey information about the material that we are going to use, the size or the dimensions of the part, and the shape or the geometric characteristics of each part. So in the drawings, we must specify the permissible variations for each of these aspects in terms of tolerances and limits. When we start adding information about material size and shape, so this is what is known as geometric dimensioning and tolerancing. So for example, here, if we have a table and the height of this table is 27 and the tolerance is given as plus or minus 1. By the way, this dimension is not according to BS8888. It's just for visualization only. So dimensions given here does not comply with PS8888 because in PS8888 we have a continuous line here and the dimensions are written outside this line. So we're given a table here with a specific height, with a specific tolerance of the height, but we understand also that the surface here, any surface, has some sort of waviness and or smoothness. So, for example, this table, if we consider this table, yes, it is within the tolerance that we have defined. So the average kind of height is 27, and the minimum height is 26, and the maximum height is 28. So it is, the inspector would say this is acceptable. If we compare it to another table, which is this one, again, just kind of the average height here is 27, the minimum height is 26, and the maximum height is 28, which will be acceptable as well. But they are not quite similar in terms of the kind of the surface that they have. So how we can just think about controlling this surface as well, the flatness of the surface. This is where we use GD&T. So one way of doing this is if we wanted the top surface here to be flatter, we can just tighten a little bit the tolerances. Instead of plus or minus 1, we could say plus or minus 0.03 mil or inches here. But this will just make a problem for us because this tightening the tolerances here is going to restrict the height of the table to 26.97 to 27.03. And this means that good tables are going to be rejected by the inspector. But we just need to think about other way of doing this, of just controlling the surface without affecting the height and its tolerances. So you can have both, like by using GD&T. So the table height, for example, may be any height between the 26 to 28, and the tabletop must be flat within 0.06 inches, for example. As I mentioned earlier, dimensions here are not according to BS8888, but I'm just trying to explain the idea. So in this case, you can have this height, which is 27 plus or minus 1, okay? And then we have here what's called the feature control frame. We're going to talk a lot about this, but this symbol here, geometric symbol, shows the flatness of the surface, and it says that this surface should be flat within 0.06 inches. This means that, for example, if the height is 26 or 27 or 28, three of them are going to be accepted, and we should also restrict the flatness of the surface to be within 0.06. So we have kind of two types of constraints now, but we still, any table that is between 26 to 28 is going to be accepted, but also we need to make sure that the flatness of the surface is within 0.06 inches to have a more flat surface. And this is identified on the drawings by what's called GD&T, or the feature control frame here. There are some definitions that you might see when you use GD&T. The first one is called maximum material condition, MMC, which is the condition where the size of the feature contains the maximum amount of material. Think about the shaft and the hole, for example. So for a shaft, the maximum amount of material means that the largest shaft within the permissible tolerances, and the maximum amount of material for a hole means that when we think about the smallest hole, so in a plate, for example, so this is where we have the maximum amount of material. The least material condition, it's opposite to what I said here. So if you have a hole, so within a plate, then the least amount of material occurs when this hole becomes the largest, when we have the largest hole within the permissible tolerance. And then if you have a shaft, for example, so the least amount of material is when you have, happens when you have the least diameter of the shaft. So the tolerance is the difference between these two conditions. The difference between the maximum material condition and the least material condition is defined as the permissible tolerance. So the allowance is that it is the difference between the maximum material condition of two mating parts. If you have, for example, like a shaft and a hole, and then you have the maximum material condition for the shaft, the maximum material condition for the hole, and then you try to assemble them together, the difference between these two conditions is defined as the allowance. The basic dimension or the basic size, if you remember from tolerances, is the nominal dimension from which tolerances are derived. For example, what are the limits of size? If we have a shaft here, and then you have been given a dimension, and then it says here phi, which is the diameter of the shaft, is between 2.007 to 2.003. But what does this mean? It just means that the shaft diameter, real diameter, could be anywhere between the least material condition, which is where the diameter is 2.003, which is the smallest diameter, to the maximum diameter, which is 2.007 at the maximum material condition. So this is the kind of the tolerance that is given, and the real shaft diameter in the end after manufacturing could be anywhere between this. This is the permissible tolerance that is given to the manufacturer. So any diameter within this range should be acceptable by the inspector. So a variation in size is allowed between the least material condition and the maximum material condition. The actual size, which is sort of the black circle here, so the actual size of the feature at any cross section must be within this size boundary. So the least material condition and the maximum material condition. So there are some symbols here we need to learn. These are the geometric characteristic controls. These are the symbols that we are going to use to indicate flatness of the surface, for example, or straightness of an edge, or circularity of a circle, or cylindricity of a cylinder, or the profile of a specific shape, or if you have a surface that is profiled, or you have two surfaces that are perpendicular to one another, or you have a specific surface at a specific angle to another surface, two surfaces that are parallel to one another. You have the run out when you have a cylinder and it rotates for one cycle. So there is what's called the circular run out, how it deviates. So for example, if you just imagine that you have a cylinder and then you have one point on the surface of the cylinder, and then you rotate this cylinder one full cycle, then what is the path of this point on the surface, how it just deviates from the theoretical circle that it should take. You have also concentricity when you have two cylinders, two concentric circles or cylinders. You have the position of a hole, for example, or the symmetry of two different surfaces. So we need to just learn about these because these symbols are important, and then we're going to use them. So if we have what's called the form tolerance, this doesn't require a datum, reference, but for the rest of these, it requires a datum reference. We're going to talk more about datums in the next session, but the form features does not require a datum, but these ones, orientation, run out, and location, they require a datum, as you will learn in a moment. These characteristics and symbols you need to learn as well. In the feature control, this is the feature control frame that shows kind of the tolerances, the geometric tolerances, but you might just see like a symbol here, like M in a circle, for example, or this symbol. So this symbol is for the position, as you've seen on the previous slide. See here, for example, this is the symbol of the position. So the position of the center of a circle, for example, should be within specific tolerance and limits. So these symbols, the M means that the maximum material condition, L is the least material condition, P is called the projected tolerance zone. This is a bit advanced, but it will take some time to explain it. But please just try to make some research about this. Phi is the diametrical or cylindrical tolerance zone. We'll talk about this more in the last session. And when you apply this GD&T for a specific dimension, we put like a box around, we put like a rectangle here around the dimension itself to indicate that it is controlled by the tolerance of this dimension is controlled by GD&T. Also, we need to use some symbols for datums. For example, A here is the datum A. So we'll talk in the next session more about datums. This is called the feature control frame. that defines the GT and T for a specific dimension. So in the feature control frame, the first one is the geometric symbol based on the table that you have seen. Then the second part here gives tolerance information, what kind of tolerance available for position or flatness or cylindricity and so on. And these three are used for datum references. So sometimes we could say the vertical surface is perpendicular to the horizontal surface, for example. So the horizontal surface here is used as the datum. So we give it a symbol like A, for example, and say the horizontal surface is datum A. And then when we define here the allowed value for the perpendicularity, we say the vertical surface is perpendicular with respect to the or relative to the horizontal surface with a specific value or within a specific value. So when you see this feature control frame, it reads like this. You say that, and then based on the symbol here, it could be the position, or the flatness, or the straightness, or the cylindricity. So based on the symbol here, you say that, and then you read this one. Of the feature must be within, so the position of the feature, for example, must be within, and then you add here the tolerance value must be within, for example, 0.06 or 1 millimeter or 0.5 millimeter relative to the datums, A, B, and C datums. We have primary datum A, secondary datum, tertiary datum, so A, B, C is the primary, secondary, and tertiary datums. So the feature control frame indicates the tolerance as follows. This is one example. For here we say that the position of the of a circle, for example, or should be within a cylinder of a diameter 0.03 millimeter when this has material condition symbol, the maximum material condition, and with relative to A, B, and C data. So in here, this shows you the feature control frame where it reads like you use first the symbol, the geometric characteristic symbol. Then the second part shows you the tolerance zone descriptor, where you show what kind of geometric tolerance that you have, what kind of material condition you have, and these are the three datums, A, B, and C, primary, secondary, and tertiary datums. So this feature control frame reads as follows. The position of the feature must be within 0.003 diametrical tolerance zone. We'll learn about this more in the last session. At the maximum material condition relative to datums A, B, and C. So again, this is another feature control frame that says it reads as follows. The position, because this is the symbol of position of the feature, must be within 0.003 diametrical tolerance zone, which given here, at the maximum material condition relative to datum A, where datum A itself should be at the maximum material conditions and datum B. We'll learn more about this as we go. It might be not 100% obvious so far, but we'll learn more as we go, and eventually you will get it in by the end. So what you need to do here, these are some sort of exercises for you to do. So you could say here, just go back to the table and then check these symbols and see what do they mean. Check the values for the tolerances here and the M condition and the datums, and then try to just fill in those missing parts here or missing spaces here. It's just an exercise for you to do it yourself. So the placement of a feature control frame, where we place it on the drawings, it can be attached to extension line, for example. So if this is the let's say this is part, and then to define the dimension, it's going to be somewhere here, and this is the extension line, so you can just attach the feature control frame to the extension line, or if it is an angle, you can attach the feature control frame to the extension line of the angle here. This is the symbol for the datum A. So the bottom surface here is used as datum A, and this is the symbol when you you identify the datums. We'll talk about this in the next session. Or here, for example, this is the extension line for this dimension here, vertical dimension. You can attach the feature control frame to this line, or you can attach it to a surface, for example. You say that the flatness of this surface should be within 0.005. It could be applied to a surface, again, similar to this one. So the cylindricity here of this surface should be within this tolerance. It could be also attached to an axis. You could say that the axis here, this axis here is perpendicular to datum A, and the axis should be perpendicular to datum A with a tolerance of 0.003 at the least material condition. Also, it could be adjacent to a dimension. For example, we have two dimensions here, and it's the right time to distinguish between these two. So, for example, you have a circle here, and you have been given like the phi or the diameter of the circle is 0.5 and plus or minus 0.005. So the circle itself here, so the diameter of the circle is 0.5, and the tolerance here, the upper and the lower tolerance values are given, which we have symmetrical tolerance here. So this circle could be within this tolerance, plus or minus 0.005, okay? Anywhere between 0.5 plus 0.005 or 0.5 minus 0.005. So this is the size of the circle itself. But this here, this feature control frame defines the location of the circle, it defines the location of the center line here. So it says the position of the center line or the position of the circle identified by its center line here should be within 0.003 here at the maximum material condition with respect to A, relative to datum A. When it says here phi 0.003, what you can do here, you just imagine that this is the center, and then you would draw a circle here, another circle, with a diameter of 0.003, okay? And the location of this center should be within this circle. It does not go outside this circle. This is the permissible diameter that is given for this center to just move within. So it can move to the left, to the right, to the top, to the bottom, or just along the diagonal, but it should be within this circle of 0.003 for this one. Okay, at the maximum material condition. So we're talking about the circle itself. The maximum when the circle is at the maximum material condition, meaning that it is the least diameter here, which is 0.5 minus 0.05, and then based on that we start identifying the location. Okay, so the form features, I said earlier in the table, the form feature does not require a datum reference. For example, these four features here, the flatness of a surface, or the straightness of an edge, or the circularity of a circle, or the cylindricity of the entire cylinder, does not require the reference to define them. So when we say like the flatness of the surface should be within a specific value or a specific tolerance. What we mean by that, we just draw like two flat surfaces, and the distance between them is the tolerance that is given, and we say the actual surface, which is the black one here, should lie within this tolerance. It should not go beyond. It should not go. It shouldn't go above or below this tolerance that is given. The same here for straightness, for example. If we're talking about a specific edge, and then we say the straightness should be within this value. So you draw two surfaces here, or two lines, and the blue one here, which is the real one, should be straight within. So if you keep drawing any line here or any plane between these two planes, regardless of its angle, it should be considered as acceptable, as long as this blue plane here does not go above or below these two planes that defines the tolerance. The same here, if we say the circularity of this cylinder should be within a specific value, 0.5 for example. So what we do, around the center line here, we draw two circles, just imaginary circles, and we say that the difference between these two circles is the tolerance that is defined, and the real circle, which is the black one, should be within these two circles. It does not go above, it does not go below this circle. As long as it is between these two circles, it's going to be acceptable. The same for a cylinder, but here, I mean, you have two imaginary cylinders with the difference between them is the tolerance that is given, and the black one here is the real one after manufacturing. So the inspector, when he checks it and finds that the cylindricity is within this acceptable tolerance that is given, so it is acceptable. It just passes the inspection test. So the form feature, as I said, doesn't require datum. So when we say here, for example, the flatness of the surface is within 0.06 tolerance zone. So what you can do here, you can draw two flat surfaces where the distance between them is 0.06, similar to the previous slide. And then the surface here, the real surface here, should be within these two defined surfaces. So if you can imagine, because we are looking at the front view here, imagine that you draw a line here above this surface and another line below this surface, and then the distance between these two lines that you've drawn is 0.06. So the real surface here can be within these two. As long as it is within these two lines, it doesn't go above the top line or below the bottom line, it will be accepted. So the flatness here, again, just imagine you're drawing two lines, one at the top, one above, one below this real surface. So this line here, or this surface here, can be a little bit at an angle to the above, to the top, or a little bit to downwards, or it could be a little bit above or a little bit below, but as long as it is within these two lines that we have drawn with this 0.03 value, it should be accepted. So the straightness of a surface of a cylinder, again, as I said, just imagine that you are drawing two lines with a distance between them, which is 0.03. As long as this line here, this edge here, is within this acceptable limit, so it should be okay with the inspector. Straightness of an axis at maximum material condition. So we have a cylinder here, and then for this one, we have the size, which is the maximum material condition, the minimum material condition. And then we have a center line for this cylinder, and for the cylinder itself, for the center line of the cylinder, the straightness of this center line or this axis is defined. as follows. It says the straightness of the center line should be within phi 0.03 at the maximum material condition. So you pick the maximum material condition, which is 0.5, and then you say that because this is phi 0.03, so if you imagine that here you draw a circle with a diameter of 0.03 and say that the line, the center line, could be at any angle, but should lie within this circle. Okay, if you look from the side view, as if you draw here two lines, one above, one below, and this axis here could be like going a little bit upwards or a little bit downwards, but as long as it is within this allowed limit, so it will be accepted. Some other features that require datum reference, for example, like orientation. If we say one surface is perpendicular to another, or one surface is at a specific angle to another, or two surfaces parallel to one another, we require like a datum reference here to define these features. So in the next session, we're going to talk about datums. So the run out, again, we require some just reference to define the run out, the location, the position should be measured from a specific datum, the concentricity and the symmetry as well. So in the next session, we're going to talk about datums to be able to define these features. Thank you.